Hey there students, Mr. Fugit here. In our video today, we're going to be doing an overview of one of our next labs dealing with forces. So as our introduction, we've really been focusing on this relationship of Newton's second law. That's been one of our primary focuses here in our study of dynamics. So today, what we're going to be talking about is how we can use some of our equipment to explore this relationship of Newton's second law. Now, prior to this, we actually have done an activity in class dealing with the low friction carts. If you remember, those were our small blue carts. And what we did there was we applied some forces on the carts and took some measurements to try and check to see if Newton's second law does hold up in the real world. Scientifically, when we're dealing with these equations, especially ones that are very important, we want to make sure that they actually do work out in the real world. And that's going to be our focus for today. Except now, our equipment's going to look a little bit different. Here we're going to have the smart carts, and we're going to use these to get a little bit better data for what we're trying to do here. But to set the table a little bit, our goal is that we're going to check the forces on an object, because remember, it's the sum of all forces on the object. Today our object is going to be our smart cart. And then we're also going to use the information the smart cart gives us to check the acceleration. Okay? Here, we're going to be keeping the mass constant for what we do, so that's not going to be a variable that we will measure initially. We're actually going to do some work and then check the mass later on as part of our exploration. So our goal, as I mentioned, is to try and look at the sum of forces on the object and see how that lines up with the mass and acceleration. That's going to be our focus. So as always, when dealing with our labs, you'll want to make sure you have the lab sheet pulled up so that you can follow along with things as we talk through them. What we're going to do here in a moment is transition over. I'm going to move to a different space in the room and kind of walk you all through how we're going to be setting things up. Hey, before we do, I want to do a little bit of work on kind of what the forces are on the cart. Now, if I just set the cart right here sitting on the track, what would our forces look like? Well, say we were to make a bit of a free body diagram here, right? Visualize our forces. Well, let's go through our list. What are our common forces? Things like friction, gravity, normal forces, that sort of thing. Well, one of the ones that we've seen most commonly is a gravitational force. As long as we're on or near Earth's surface, then we'll have a gravitational force from the Earth on our object. That's our smart cart. Now, what else? Well, the smart cart is in contact with the track, so there will be a contact force or a normal force upward. Now, what else? Right now you might not be able to tell what's going on here, but I want you to think back to what we did in our last lab when we pulled on the low friction carts. Here we're going to be doing something pretty similar, except we're going to be using these magnet attachments. Here in a moment I'll show you, we're going to use a string mechanism that we're going to attach to the magnet that will pull the cart forward. So what we're going to be doing is we're going to be pulling the cart. Now, according to how it looks for you all, we would be pulling to the left. That may change when I set things up here on the table. I might be pulling to the right, but you'll get the idea. We're going to apply a pulling force. Now, the reason we're doing it this way is because one of the issues we saw in our last activity was it was hard to get the pull force to be consistent, right? When using the spring scales, it's hard to make sure we're right at 1 Newton or 1.5 newtons. Using things here with the smart carts and using the string is going to be a lot more, hopefully a lot more consistent. We'll see how the numbers end up shaking out. But our goal is to try and get kind of a better reading on what we're doing. Not that what we did last time was terrible, but there were some inconsistencies with what we were doing there. Even still, we still saw a pretty good relationship there. So our goal is to try and see if the sum of our forces will equal our mass times our acceleration. More specifically, what we're going to do toward the end of today is we're going to generate a graph of force versus acceleration, and we'll look at what the trend shows us. As we've talked about earlier with Newton's second law, what Newton's second law predicts is that our sum of forces, as that value increases, let's say we keep the mass the same, which we will today, as our sum of forces goes up, our acceleration should go up proportionally. There's a linear relationship between the sum of forces and the acceleration. So what Newton's second law predicts should happen is that we should see a mostly linear trend as we increase the force on the object to its acceleration. But this is what we're trying to explore. Does Newton's second law actually work out in the real world when we're collecting data and not just when we're talking about it more conceptually? This is going to be our goal for today. So we're going to transition over now, and I'm going to show you a bit of the setup on what we'll do, and as well as I'll go through and collect some data, and then we'll actually walk through how to use that data to try and check and see what's going on with Newton's second law. We'll walk through generating our graph and how you'll be able to do things remotely on your own. So we're going to transition over now and see how we can set things up. So as we've talked about, our goal here is that we're going to be looking to check Newton's second law. Now, in terms of our setup, here's how things are going to look a little bit different than what we did last time. As we talked about, now we're dealing with the smart carts rather than the low friction carts. Now, if we just have the smart cart here at rest, and what I may take a moment to do is I'm going to go and level out my track. You'll notice the cart is sliding a little bit this way. So I'm going to raise this side up just a bit. Hopefully that will help us kind of level things out a bit. There we go. Okay, so now that I've got my track leveled, there are forces acting on the cart right now, namely a gravitational force from the earth on the cart and a contact force, a normal force, from the track on the cart. Now, if I leave the cart right here, then it would appear the cart is at rest. And according to Newton's first law, the cart should stay at rest, unless one of those forces changes, our normal force or our force of gravity, at which point our system may change a little bit. But for now, those forces seem to be relatively well balanced. Now, what we're going to do is we're going to pull on the cart, very similar to what we did in our last lab, except rather than using the spring scale, we're going to try to use some of the tools we've got with the smart carts to be a little bit more accurate and consistent. So here's what we've got. I've got this little string here that's connected to an O-ring. Now this is metal, so I can hook it into that magnet attachment here on the end of my smart cart. So this device here, and I should have probably showed you all this. This device here is just one of the many attachments that comes with our kit. So this portion here, this magnet attachment, can thread in to this open end of the smart cart. Now that open end down here, this is opposite of the plunger, that open end is actually a force sensor. Now we haven't used that much, really I don't think we've used that yet at all, but I'm going to show us how we can enable that so we can take direct measurements on force. Up until now, the only things we've used the smart carts for have been things like position, velocity, and acceleration, which are great. We've done some awesome work with those, but we can actually do even more. So I'm going to go ahead and just kind of attach my string to the end of the smart cart. I'm going to put this at one end of the track, and you'll notice, move these things over just a little bit so you all can see a bit better. You'll notice at the other end of the track is a pulley, right? Now I'm actually going to, if I can, I'm going to adjust this a little bit to where that's actually hanging over the edge of the track. Now what I can do is, if I let the smart cart go, wasn't centered on the track. You'll notice that it might start to pull just a little bit. Now, one thing we may see is that there's not really enough mass to really be pulling on the cart significantly. But what we're going to do is we're going to attach some masses to one end of the string like so. And then you'll notice if I let the smart cart go, that's going to cause an acceleration, right? There's going to be a net force, an overall force in this direction toward your left, and that's going to cause the cart to accelerate. And we're going to use some of the tools of the smart cart system and the software to check the data for us. So I'm going to go ahead and take this off for just a moment, and I'm going to come over here and show you all a little bit of how we'll set things up with Vernier. So real quick, I'm going to come over here, and hopefully this will show up on your screen if I can get that to work properly. And I'm going to do a few things. Number one is I want to make sure I enable the force sensor. The cart does have a force sensor, but basically unless we turn it on, it's not going to work. So down here in the bottom right corner, I'm going to click on my sensor setup tool. I'll click there, and you'll notice under the sensor channels, it only has the position sensor enabled. So I'll go ahead and click force, and then I will hit done. Now, down in the bottom corner, I will see both the position for the green cart and the force sensor for the green cart, both that have been enabled. Okay, now a couple other things I will do. I'm going to go ahead and take some masses and add these to my cart. This will make things actually a lot easier to work with. So, okay, I'm going to take some masses. I'm going to add them to my cart. Add those in. This will give the cart a little bit more mass, so it's hopefully going to make things a bit easier to work with. And last thing I'm going to do, back over on Vernier, I'm going to go down here in the corner, and I'm going to zero out both of my sensors. The position sensor won't matter as much for what we're going to do because we primarily want force and acceleration. It will still be able to get a good acceleration regardless of what the position is. I definitely want to make sure I zero out my force sensor because when I attach the string in, there is a little bit of a pulling force, and I want to make sure I zero that out. I want to assume that right now there's no pulling force. I only want to measure the pulling force once I start to add mass on the end of the on the end of the string. So for what we're going to do today, we don't want to exceed about 100 grams. So I might try 20 and just kind of see what that does before I start recording anything. Okay, that looks pretty good. So here's what I'm going to do. I'm going to attach this 20 gram mass on the end of the O-ring on the other side of the string. That's going to cause a tension force, a pull force on the cart, and the cart should accelerate as a result of that. Now, to help me keep track of things just a little bit, I'm going to write down what my masses are. This is something you would want to keep track of. So first mass I'm going to use is 20 grams. Okay, so I'm going to attach my mass, and then I'm going to hit collect and get things going. So here we go. 3, 2, 1, collect, go. Okay, now I'm going to hit stop there. Okay, so things look pretty good. I'm going to come over now and kind of look at how my data looks. So let's look at this for just a moment. Okay, so it looks like I'm going to look at my force values up here. I'm going to go ahead and turn my position off. So I'm going to go to my options up here, and I'm going to go to 2 graphs. Okay, so I want force and I want acceleration. Turn position off. Okay, so it looks as though if I kind of zoom in on my force graph up here, it looks like my force is hovering around 0.21, 0.2. Now, in order for me to get a better average, what I can do is I can click and drag across, looks like about here's where things are constant, about half a second up to about 2.5 seconds. Okay, and then I'm going to go down to my graphing options and I'm going to hit view statistics and look at my mean, which is going to be my average. So my force here is going to be 0.2 newtons. That's going to be this number, about right in there, 0.2 newtons. So there's my force applied onto the cart. And then if I look down here at my acceleration graph, you'll notice this is a little bit more noisy. The graph looks a bit bumpier. There's probably going to be a bit of a spike. That's going to be right here when the cart first jumps into motion, like it first begins to accelerate. And then you'll notice that the acceleration is roughly constant across the track, and then it starts to stop here. What's happening at that point is the string is actually probably going to hit the ground, which is going to affect what happens with the tension force. So I really only want to get data from about here to about here. So I'm going to go ahead and click on the end of that range, and then select back to about here. That looks pretty good. I'll hit my graphing options, view statistics, and then what I want here is I want the mean. That's going to be 0.184 meters per second squared. I'm going to write that down, 184 meters per second squared. Okay, so I've got my force and I've got my acceleration. Now, as generally as the practice, we want to get multiple measurements at each individual testing condition. Now, we generally do that when we have things like the low friction carts or objects that are moving that we don't have really good equipment on. But when we've got the smart carts, we actually have a pretty good setup here that we won't need to collect this data point over and over and over and over. So now I'm going to come back over, I'm going to change my mass, and we'll see how things look. So now I'm going to go with 40 grams. So I've got two 20-gram masses, and I'm going to stack those on my rate. I'm going to hold my cart in place. Okay, so I'm going to go ahead and get things ready, and we'll go collect in 3, 2, 1, collect. Okay, you can stop there. Okay, again, the cart is probably going to stop, or at least slow down before hitting the end of the track. I have my hand there because I want to make sure I don't damage any of the equipment, but the string is probably going to hit the ground before it gets there, which is okay. We just want some nice range where we can see the force and see how the cart is accelerating. Okay, so now I have a mass of 40 grams. Okay, so I'm going to look back over here at Vernier. I'm going to go and select my range. Looks like I'm going from a little over 1 second. Okay. trial 2 going on here. Here's statistics. Okay, looks like our mean force was 0.217 newtons. Okay, and then we'll look at our acceleration here. And again, this one's a little bit more noisy. That is okay. We'll do our best to get an average. Click on View Statistics. And it looks like we have an acceleration of 0.219 meters per second squared. Okay, so what I'm going to do now is I'm going to go through the process and get the rest of my values. If you want to continue watching this section, feel free. Hopefully this now gives you an idea on how I'm going to go through and get each of my data points. I'm just going to go through and do this 3 more times so I get enough information to be able to generate my graph of force versus acceleration. So again, if you want to continue watching, I'll show you how I get the rest of my data points. But if you want to skip ahead a little bit in the video, our next goal is going to be to take our measurements here and then put those into a graph and see what our graph looks like. Okay, so I'm going to get things set up again. Come back over here. And now we want to go to, I may just keep this pattern going. I've done 20 grams, 40 grams, now I'm going to do 60. So I'm going to get a 50 gram mass and a 10. So 50 and 10. Okay, I'll get my cart set back up, back at the end of the track. Okay, and attach my 60 gram mass. And here we go. We're going to go, okay, 3, 2, 1, I'll go collect. Okay, so again, the action is going to happen a lot quicker as that force starts to go up and up and up. Pull this, it's got jammed a little bit in there. Sometimes that can happen with the string. A little bit of a knot there. We'll adjust that. Oh, goodness, having some issues there. Okay, so I'm going to check my numbers here. Looks like my acceleration, again, this is all going to happen a lot quicker because the force is increasing. So View Statistics, looks like my average acceleration here, 0.609, noticeably bigger, meters per second squared, and force, average force there. Okay, go to View Statistics, and I'm looking at 0.527. Now, as I'm doing this, I'm noticing there was a really big change from 40 to 60, whereas from 20 to 40, the change wasn't as big. So what I may do here is I may go ahead and repeat my 40 gram trial just to be on the safe side, because I'm wondering if I didn't hit collect at the right time, that sort of thing. So I'm going to just check this once more. Okay, let's do the 40 grams again. 3, 2, 1, collect. Okay, I'll hit stop there. Okay, so I'm going to check this once more, and I get my average of my acceleration. Come over here. It's coming back. Okay, yeah, that looks like a little bit more in line with what I would think. I've got 0.409 meters per second squared. So kind of what I'm seeing there is like about 0.2, about 0.4, about 0.6, and then our average force for this trial from the pulley was 0.362. Okay, that seems a little bit more reasonable. 0.362 newtons. Okay, again, I was thinking there might have been a little bit of an issue with how I collected things. I might have actually been grabbing the data improperly, which again, can't happen. I mentioned earlier that when we're working with the smart cards, we don't oftentimes need to collect data as many times just because these give us usually really good data. But again, if we're seeing something that doesn't seem to fit, and I kind of have an idea what I think this should look like, we can go back and recollect that just to make sure, are the numbers actually accurate? So I've got my 60 gram mass trial. I'm going to do 80 and 100. So for my 80, I've got a 50. I'll do a 20 and then a 10. Okay, and I'll get my string set up over the pulley. There may have also been an issue with how I set things up with the pulley. Sometimes the string can become kind of dislodged or off center there. Okay, so let's get our string here. Okay, this one again probably is going to happen pretty fast, so we'll see. Here we go. 3, 2, 1, collect. Okay, stop there. Okay, so again, action's happening, or the acceleration's happening very quickly. So our average force from the string, we're looking at 0.693 newtons. Okay, and then our average acceleration, view statistics, we're looking at 0.828. Okay, so seeming to be pretty solid there. Okay, and then our last one, we're going to go with a 100 gram mass. I have a nice one mass that is 100 grams, so hopefully this should work well for us. Okay, last trial, here we go. 3, 2, 1, collect. Stop there, again, happening very quickly. Okay, and we'll check our force. Get my average there. Okay, and looking like 0.857 newtons. And then our acceleration, and that window's getting a little bit more narrow, and 1.024 meters per second squared. Okay, so now that we have all of our data points, we're going to transition over now and look at how we can make a graph with those data points. And it does look like, just from kind of a cursory glance, as my force goes up, my acceleration goes up, which very broadly, more generally supports Newton's second law, but it's not just that we want to see a direct relationship. We're specifically looking to see, is there a linear relationship? As I increase my sum of forces, my overall force in this direction, is there a linear increase in our acceleration? That's what we really want to try and see. So we'll transition over now and see how the data actually shakes out. Okay, so now that I have my data, I've come over here to Google Sheets and I'm going to work on generating a graph of force versus acceleration. By looking at my data points, I can see, as I mentioned a moment ago, broadly, that the numbers seem to be supporting Newton's second law. As I increase my force, I'm seeing a noticeable increase in my acceleration. But beyond that, we want to look for, does the data show a linear relationship? So I'm going to go ahead and input my data here. I'm going to have force versus acceleration. So I'm going to go ahead and put my acceleration first, meters per second squared. Okay, and then I'm going to, if I double click there, that should, adjust my spacing, force versus, force and acceleration. So I've got acceleration of 0.184 and then 409, and then I've got 0.609, I've got 0.828, and then 1.024. Okay, and then my forces, I had 0.2 newtons, and then 0.362 newtons, 0.527 newtons, 0.693 newtons, and then 0.857 newtons. Okay, so I'm going to go ahead and generate my graphs. I'm going to select all of my data points. I'll hit Insert and Chart. Okay, and we'll see how things look. Hopefully it will recognize I want a scatter chart, but sometimes it doesn't. Okay, great. And looks relatively linear, force versus acceleration. Okay, so, and looks pretty good. Got my scatter chart in here. Looks actually really pretty solid, very linear. And I'm going to go ahead and go over here to Customize. I'm going to go to Series, and then I'm going to go down to Trend Line. Okay, and again, data looks actually very solid here. Now, one last thing I'm going to do is I'm going to get an equation for that trend line. I'm going to hit Use Equation here. Okay, so I'm going to use this, get this equation, and I'm going to go ahead and write this down. So it's looking like what I've got here is 0.786x plus 0.0494. So y equals 0.783x plus 0.0494. Okay. So I have a pretty solid looking graph here. It does appear to be linear, and I've got an equation here to show me the trend line. Now, one thing that you'll notice is my y-intercept seems to be very, very close to 0. It doesn't appear to be showing that on my graph. One thing I will show you all real quick is if I come over here to that would be my horizontal axis, my x-axis. I'm going to go ahead and I can put for my minimum value 0. And what that will do is that will actually show where 0, 0 is so that I can see what the origin would be. Sometimes it may look like your graph should or shouldn't go through the origin, and we'll talk a little bit about that in part of our analysis. But it looks like our graph actually pretty closely, and it goes to the origin. Again, we have a very small y-intercept there, which is actually really good. We're going to talk about that. So I've got my graph here. We're going to come over now and kind of finish out some of our discussion together, and we'll wrap things up here with our lab. Okay, so now that we've walked through some of the analysis, let's talk a bit about the interpretation. What does all of this information tell us? Well, I've got my graph actually pulled up here. Let me come back just real quick. Okay, so our goal, as we talked about at the very beginning of this video, our goal was to check to see, does Newton's second law actually work in the real world? Is this a true equation for what's happening? Because really that's kind of the goal of what we're doing in science, is we're trying to figure out what's actually happening in the world, what's really going on in the universe, and can we model that? Can we figure out what's actually happening from a mathematical standpoint? That's really kind of at the core of what we're doing, with all of science, and we, again, go back to Newton's laws for a lot of those ideas. So, our goal, as we mentioned, was to see what is the sum of forces on our object, and does that actually equal a m times a? Now, for what we're doing here, the mass was effectively a constant value, so what we really did here was we increased the amount of force, we pulled with more and more force to try and see, does our acceleration increase linearly? Does it match that relationship? And as you all can see from the graph here, it might not be as easy to see here, but we have a very good linear relationship here. And this graph is actually the evidence that we're looking for to support Newton's second law. The fact that we increased the force, and that pulling force was kind of our sum of forces, well, not kind of, it was our sum of forces, and we see a linear increase in our acceleration, that shows us Newton's second law is actually, well, valid. We can verify that. Now, beyond that, what do these numbers mean with the equation? Because that equation is actually very important. I'm going to write that down over here. So I've got this graph of force versus acceleration, FVA. Okay, now I have an equation that matches my trend line. I had a trend line that looked about like this, and my trend line looked pretty solid, and my equation is going to be the equation of a line in slope-intercept form. Now on sheets, you only see this point something something x plus something else. It's really y equals mx plus b. It just looks a little bit different. Now back to over here. So my equation is y equals 0.783x plus 0.0494. Now what do those numbers mean, and how do they help us understand what's happening? Well, think about how we set up our graph. What is on the y-axis? The y-axis is our pulling force. Now, remember, with Newton's second law, the idea is the sum of forces is equal to n times a. Now, for our purpose, as we talked about a moment ago, or kind of way back at the beginning, we're looking primarily in the x direction, right? There wasn't really any acceleration in the vertical direction because, well, the track was level, so the cart was just moving horizontally. So for our purpose, we're kind of ignoring the forces that happen in the y direction. Not that they're not there, but they're not contributing to the acceleration in the x. So our focus is we're looking at the sum of forces in the x direction is equal to mass times acceleration in the x. Now, what is our sum of forces in the x? Well, we just had our pulling force, right? Now, theoretically, there should be some other forces in the x direction. Namely, maybe a little bit of air resistance, and possibly some friction. But as we've seen before, the tracks are actually, well, pretty solid examples of a frictionless surface. They're not perfectly frictionless, but they're very, very, very low friction. So while there may be a little bit of air resistance, for the most part, our sum of forces should be our pull force minus maybe a little bit of air resistance. Now, how does that relate back to what's happening with our equation? Well, what's on our y-axis? That's our overall force on the cart. So what if I rewrote the equation like this? The y-axis is my force, which should be my sum of forces here, because the only real measurable force we have is the pulling force. There's a little bit of air resistance there, but as I'll show you in a moment, it's actually very, very small. Is equal to some value, 0.783, multiplied by my acceleration. Well, on the x-axis is our acceleration. So this number here, the slope of that line, should be an approximation on our mass. Our slope should be an approximation on our mass. Now remember, how do we find slope? Like, let's say we didn't have Google Sheets to be able to do this for us. How would we find the slope of that line? Well, in that case, what we would do is we'd have to choose 2 points on our line, right? And then we'd have to use our slope formula, something like y2 minus y1 over x2 minus x1, and that would give us our slope. Now here, slope is just represented with a general m term. That doesn't mean the slope of every graph we look at is going to be our mass. M is just the general term we refer to a slope as. Okay? Now, think about the units of what that number would be. What's on our y-axis? Well, this is our sum of forces in newtons. On the x-axis, this is our acceleration in meters per second squared. So a newton divided by a meter per second squared, well, Newton divided by meter per second squared. Well, remember, a Newton is just a kilogram meter per second squared divided by a meter per second squared. So the meters per second squared units would cancel, and we should be left with units of kilograms. So our slope should have units of kilograms, meaning it should be our mass. Now, I'm going to take my scale and we'll check that. So, put my cart on the scale with the masses, and the number I get is 792 grams, or 0.792 kilograms. So I'll show you something real quick here. The actual mass is 0.792 kilograms. The experimental mass, meaning the number we get from our experiment, this would be our slope, is 0.783 kilograms. Now, those seem to be pretty close, but let me show you just how close those values are. You may have learned at some point in a class how to find percent error. Here's what you can do. To find your percent error, we're going to take the difference between our actual and our experimental, and we treat that oftentimes as an absolute value because we're not really concerned whether we're above or below. We just want to see how far away our experimental value is from the actual. So I'm going to take 0.792 kilograms minus 0.783. That's the difference in what I predict versus what the real number is. And then I'm going to divide by the real number. Because I'm figuring out how many kilograms I am away from the real mass as a percentage. Okay? And then I'll multiply by 100. So 0.792 minus 0.783, that gives me 0.009, divided by 0.792, multiplied by 100, and my value here is 1.14%. So that tells me that the mass prediction I made was 1.14% away from the real mass, which tells me I'm getting a very, 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 very good measurement on what's going on there, right? Significantly better than I would get just from pulling on this with my own hand. So, number one, that's one of the main big takeaways that we want to have. That not only is our graph linear, force versus acceleration, that graph can also tell us what our mass actually is, what it should be. Okay? Now, last thing here, what is this other term, this y-intercept value? That's going to be this b term. What would this be? Now, if you remember, a y-intercept, that's where your graph would cross the y-axis. So what this means is, if I have no acceleration, I would have a little bit of a force. What does that mean? Well, here's what that means. That means my graph is crossing about here. All right, so when, at this point, I've got zero acceleration. So zero acceleration and 0.0494 newtons. Now, what does that point mean in the real world? Well, here's what that point means. That point means that there's a little bit of a force we can apply before we start to accelerate. Here's what that means. We're assuming that the cart and the track are a frictionless surface. In reality, there's probably a little bit of friction there, meaning we can pull on the cart a little bit. We have to overcome that little bit of friction before the cart starts to accelerate. We haven't done a whole lot with forces of friction yet. That's okay. We're just talking about this more conceptually. The concept is I have to overcome a little bit of friction to get the cart to accelerate. And that little bit of friction is 0.0494 newtons. which tells us the amount of friction on the track is very, very, very low. So our assumption that the track is frictionless is actually supported with that number. That number tells us that that friction is very, very, very small, meaning for the most part, we can ignore it. So overall, this graph and this equation, and even the mass that we're getting there, and that y-intercept we're getting, are all great confirmations of everything that we're trying to see. The fact that our graph of force versus acceleration is linear, that's support for Newton's second law. And the fact that we're able to use that to get a mass that's within 1% of the real thing is also really good support for Newton's second law. So hopefully, at leaving this activity, things we want to take away, Newton's second law does actually work in the real world. It's not just an equation that sounds good, or that's good in theory, but in practice, when we actually apply this, it does work. And not just in these systems, but in every system we've been able to look at thus far. Newton's second law is a valid approach for mathematically understanding the force and the acceleration, or the sum of forces, and the acceleration on an object. So hopefully this gives you the things that you need if you're working through things remotely. As always, if you have questions, feel free to reach out and let us know. Other than that, good luck.